All right. Well, thank you for having me. It's really a pleasure to be here. I see a lot of familiar names in the participants list, so thanks for coming. It's a pleasure to do this. I even see my dad, which is awesome. Um, so tonight I'd like to present to you something from your own backyard for most of you there in the Coast Geological Society. Um, and this is being presented with Marc Kamerling and Michael Gross, two longtime colleagues and friends of mine that I have worked with for quite some time, both in industry and academia. And we're presenting tonight on petroleum migration in an active petroleum system. And although this may seem familiar to much of the world, this is a very, very unusual um, area where you can actually see these processes working. So the presentation here is largely based or extracted from two recent publications. On the left is a new Pacific Section APG volume that was created for the last conference. It was actually supposed to be in Oxnard in the last spring, but then had to be canceled due to the pandemic. And it contains 4 separate field guides, including papers by Tom Davis and Jay Nampson on structural traps along the San Andreas Fault, Tess Minotti and Steve Graham on the Salinas Basin, John Schwalbach and Kevin Bohawks on the Shell Beach section and source rocks, and a paper by Marc Kamerling and me that I'm going to be going through today. But it also is contributed from another volume in 2018 that was published by the National SCPM called Stratigraphy, Diagenesis, and Structural Deformation of Monterey Formation, Central California Coast, with Michael Gross. So Marc Kamerling and Michael Gross are large contributors to what I'm going to share with you today. So just to refresh to some of you, because I know we have some people there that are in the petroleum industry or government, and I know other people that are there that are not in that field. So the petroleum system describes all the elements and processes that are required for oil to accumulate in a trap that then can be tapped by conventional oil exploration and development. And so you need a source rock that's organic rich. You need a migration pathway or route, which was what we're going to be talking about today. You need some sort of reservoir rock that could store the oil in pore spaces or fracture spaces. You need a seal that keeps most of it in that reservoir rock. And you need some sort of trap that concentrates the oil into one area so that it can be economically extracted. But besides these elements, there's processes involved, and those processes are generation of the hydrocarbons by maturation of the originally marine or lacustrine organic matter. There's migration out of the source rock through the migration pathway and ultimately into the trap. There's its accumulation, and then there's preservation, because all traps leak and eventually they get eroded and the petroleum that's trapped within them gets destroyed. This is the conventional petroleum system. And that's a good reason for us to study petroleum migration, which we're doing. We're going to be looking at today, but there's another reason too for those of you that are not particularly into the petroleum industry, and that is the carbon cycle. And the carbon cycle is critical to so much of the challenges and the understanding, the scientific research that we have to do today. And so there's kind of a couple speeds of the carbon cycle. The fast carbon cycle takes place on a daily, yearly, decadal time scale. And this relates to changes in land use, agriculture, fires, production of hydrocarbons and burning them, generating our energy, take up of that CO2 in growing plants on land and in plankton in the ocean, and dissolving back into the ocean and stuff. This is really, really fast. This is human time scale type changes. And often this is even proceeding at rates that we don't quite put our hands on well, because we don't see where the carbon's moving at any one time in particular. But then there's a slow carbon cycle. This is the geologic carbon cycle. And this absolutely controls climate change on the long geologic time scale. So over millions of years to tens to even hundreds of millions of years, the movement of carbon from CO2 in the atmosphere to take up during weathering of silicate and carbonate rocks that are exposed at the surface, to being transmitted into organic matter or calcium carbonate and being buried in sediment, burying that, then taking it down with plate tectonics, ultimately to be metamorphosed or to be melted and subducted and then come back up to the surface, or maybe being uplifted by tectonics to be exposed again. This is what controls CO2 in the atmosphere on long time scales. And this is what has, for most of Earth's history, controlled our climate. But petroleum is this one fast part of the system. And petroleum migration itself kind of short circuits the slow geological carbon cycle, because the organic matter that may have been buried deeply in the earth does not have to be slowly tectonically uplifted back up to the surface to be oxidized like it would when it's still in the rocks, when it turns into liquid or gaseous hydrocarbons, and they're able to migrate up through the rocks to reach shallow burial or even the surface in seeps, like they do so many places in California. So we're going to be studying that migration here. So most petroleum geologists, no matter how, around the world, no matter how experienced they are and how much work they've done, they have looked at reservoir rocks, they've looked at seal rocks, but most of them have worked their entire lives without ever actually seeing petroleum migration, that important process. And so when we do take people from around the country and around the world out here to California, they're seeing something that they really cannot see very many other places in the world. So there's a number of different migration pathways. One is along the damage zones that are adjacent to faults. And we're going to see how that really isn't usually along the fault themselves, but it's along the fractured rocks that are straddling the fault, that are on either side of the fault. Through fractures or brecciated rock beds, so they can go along strata or even cross strata through fractured rocks that are not associated with fault zones, but are just through deformation of brittle rocks. And then finally, kind of the more traditional way that people think of it is within and through sedimentary rocks, sandstones, carbonates, things like that, that are porous enough and permeable enough that the hydrocarbons can move through them because of their density differences. So this wonderful place for us to see the migration in action is this Ventura-Santa Barbara Basin, which runs from all the way over here to about the I-5 and the eastern part of the Ventura Basin, out from land, out into the ocean, into the still submerged western part, or the Santa Barbara Basin, often referred to as the Ventura-Santa Barbara Basin, as one continuous trend. And this trend is within rocks that have been highly deformed. And you can see in this cross section that runs north-south, all of these major faults, most of them thrust faults, or at least currently thrust faults, even if they had an earlier history as normal faults or strike slip faults, the folded rocks, and the tremendous difference in depth. So for instance, you have rocks that can outcrop in the surface here and be at 10,000 feet, 20,000 feet, just a few miles or kilometers away. The other thing about this, the system is everything is going on right now. And that's another thing that makes this really, really unique. Most petroleum systems that are studied by oil geologists and oil companies and academics that work in that field are ancient systems that generated oil a long time ago. And then the oil migrated a long time ago and got trapped. This system here in the Ventura-Santa Barbara Basin is in what we call the critical moment right now. It is building the anticlinal traps right now. It is burying the organic matter to generative depths and creating the oil and gas right now. And that oil is migrating up through the section and filling these traps as we speak. And some people have even reported areas in the Ventura anticline where they could identify areas that they've produced and then get refilled by the oil some years later. So we're going to take a field trip this evening, or at least prime you for taking a field trip on your own, and where you're going to visit 3 different locations. And these 3 different locations at Carpinteria Beach, Arroyo Burro Beach, and Gaviota Beach are going to be giving us great insight into 3 different pathways for petroleum migration in the damaged zone of faults, through fractured and brecciated rocks in an anticline, where they're traveling up dip, and in interbedded coarse grain siliciclastic sandstones conglomerates within the fine grain rocks at Gaviota Beach. Because these are all beach outcrops, if you guys go on out there themselves, it's really important to pay attention to the tide tables. Definitely at Arroyo Burro and Carpinteria, you want to be at less than 4 feet tides, but really for all of these, you'd like to be down at about 1 foot or less, especially at Gaviota if you want to go look at the outcrops there. So we're going to start this field trip from your typical meeting place at the Poinsettia Pavilion in Ventura. And we've got a 25-minute ride up the coast across the Ventura anticline, Ventura Avenue anticline, and through several oil fields. And we are gonna get off in Carpinteria, and you can either go to the state park and pay their fee and go in, or you can go down and park on a residential street and walk across the train tracks near Tar Pits Park. So here we are in a satellite image. You can drive down Calle de Ocho, which is just east of the on-ramp, off-ramp from the freeway. And you can drive to the end, park here, and walk across the train tracks and do this excursion, which runs from in the state park to, you can go on over to the other side of the old oil servicing pier that was Chevron and then Veneco. The extent of the excursion goes from here to here. These are in outcrops along the beach where they're not covered by sand or by marine terraces or the Monterey Formation. And this location is between and adjacent, very close to, a number of faults. We have the Rincon Creek Fault. We have the Carpinteria Fault. And we have some, on this map, which is a Dibley map, some splays of the Red Mountain Fault that are mapped in this area. So we're very close. This is just 1,000 meters here. So we're within a half mile or so of a couple different faults. Now here in cross sections from south to north, you see where Carpinteria is. So it's occurring next to that Carpinteria Fault. And here's the Red Mountain Fault offshore here, in these steeply dipping beds. And the Monterey Formation is at 20,000 feet, just a couple kilometers offshore. So it's in the generative window, just a few kilometers away, and the oil is able to migrate up till it intercepts these faults and then either go along the fault damage zones or across them into other strata. Here's another map, a little bit more blown up and zoomed on in of the location. Carpinteria is here along the beach in this area between the Red Mountain Fault, the Carpinteria Fault, and the Rincon Creek Fault. So faults are really important in petroleum geology. They often serve as seals where they offset permeable strata and put them and juxtapose them against impermeable strata, like sandstones against shales or mudstones. And they also are impermeable because the more that they have slipped, the more cataclasis there is right in their fault core, and also often diagenesis there as well, and they become very, very tight and impermeable. But the zones on either side of them are zones of very, very high strain rate. And often the rocks there are highly deformed and highly fractured. And this is called the damage zone. And there's been lots of studies that shows that the width of the damage zone is proportionate in a log-log relationship with the amount of total displacement there's been on the fault. And so when we're thinking about petroleum migration associated with faults, it's not really along the core, it's not really along the fault itself, but it's in these highly strained and damaged rocks, at least for the most part, that are associated with those faults. So within the damage zone, the rocks are intensely deformed. Usually faults are not a single surface, slip surface. There's many, many slip surfaces. The rocks are folded and faulted. And one of the reasons that I love looking at the Monterey Formation for structural work is that being thin bedded, you can see the deformation very, very clearly. And you can see that the rocks here are folded and shattered and faulted, many, many places in this outcrop here, tightly folded. And then all the brittle layers, which here are highly siliceous porcelanites, are intensely fractured as well. But in areas of high strain rate, it kind of blows your mind, because even really soft and porous rocks, which normally are so weak that they cannot fracture, that they can only compact or shear, or sometimes extend and normally fault, can actually fracture and have open fractures that allow hydrocarbon migration. So this is a calcareous diatomaceous mudstone. It's an exceedingly soft rock. You can put your fingernail on it and scratch it. And yet it's been strained so much that it's been intensely fractured, and the black is the hydrocarbons coming up through all the fractures. And on a warm day, or if you're in the right place, that oil just came flowing on out of the rocks in this area. So this is one of the most famous oil seeps around in California, of the many, like La Brea tar pits and things like that. And so there's areas where there's more major fractures that are putting a greater flow rate through the Monterey rocks, which are exposed here in this low bluff or low cliff, or this vision of it here. And the fractures come on up through the rocks, but they flow on up. They're under enough buoyancy and pressure that they flow on up into overlying sandstones, which are marine terrace and fluvial terrace sandstones, charge them, and then flow out under gravity and flow out over the cliffs. And certain areas where that's localized, there's a considerable amount of flow, and you see these structures that are built up as they accumulate the sand and stick to the sand. Very, very high rates. And of course, probably most of you know that this whole area was mined for the oil saturated sands as a natural asphalt for roads since the 1875 till about 1920. Transport up to San Francisco and down to LA for road building. And of course, these seeps were used by the Native Americans for glues, waterproofing, attaching arrowheads, all kinds of things like that. In the beach, you can actually see between tides and different days, you could see the oil seeping up from places where maybe there's two crossing fractures, so a little bit greater flow, where the oil's coming on up, buoyantly rising up through the sand and forming little sand volcanoes of the hydrocarbons. And these volcanoes are, you got to be careful of them when you're walking around, and they're fresh oil, they're quite fluid. But then as the waves come up or the tide goes down and the loose sand washes away, you see that they've built these beautiful volcano neck or stalk-like features here that are underneath the sand, and this loose sand's carried away. And you can see that these were locations of hydrocarbons coming up, and basically they're sticking or cementing all the sand together. So these are something that are great to go look for after we've had a storm or some period of high swell and waves coming on in, where you can erode away the loose sand around them. So Carpinteria was a great example of very, very focused hydrocarbon migration in the damage zone along some major thrust faults, the Red Mountain Fault, the Carpinteria Fault, the Rincon Creek Fault in Carpinteria. So we get back in our cars and we drive another 22 minutes to the west through Santa Barbara, get off at Las Positas or one of the other streets here in Santa Barbara, come over the mesa, and we can either come to Mesa Lane, to the steps, or come on over here a little farther west to Hendy's Beach or Arroyo Burro Beach. Arroyo Burro Park is there to look at the Arroyo Burro section, which is just west of Santa Barbara. And here's a geologic map, USGS geologic map, and the exposure is along the coast here from the Mesa Lane stairs or steps to Arroyo Burro Beach and parking. And this is on the flank of the Mesa anticline, which runs through the area called the Mesa, the Santa Barbara Mesa. There's a thrust fault that outcrops in places, the La Vigia Fault as well. And what's really awesome about this walk, and very often we go down at the stairs and go out and come back because parking is often easier than going to Arroyo Burro, or sometimes in large groups we'll come in a bus, we'll get dropped off here and the bus will meet us and we'll do a one-way walk to Arroyo Burro. And what's really nice about this is that this exposure is an oblique exposure through the flank of the Mesa anticline. So you're walking along this flank, and as you walk, you're getting different views. You're looking along the axis or parallel to the axis and perpendicular to the axis. And if we go out over here where this X to X prime line here, cross section, is mapped, and we are looking to the northwest, we're actually looking kind of along strike, and we're looking along the axis of the Mesa anticline. And this below is the cross section that's projected onto that single line, even though it's actually exposed very obliquely along the whole coast here. And you see that this side of the anticline is composed of a whole bunch of parasitic drag folds and a large number of thrust faults for the most part in this perspective. So this is showing the shortening, the northeast-southwest shortening that's prevalent across the whole Santa Barbara fold and thrust belt, which is the direction of maximum strain of sigma 1 in this area regionally as well. And so you're seeing that folding and that shortening. And the rocks are being actively deformed. Just like we said, everything's going on in this basin right now. And the rocks are being folded, as we just saw, but they're being faulted, but they're also being fractured. And how they behave depends upon their mechanical rock properties. And so those rock properties are dependent upon the original sedimentary composition that was deposited, plus the degree of diagenesis that related to burial for the most part in these kinds of rocks. So for instance, cherts, which are very, very pure diagenetic siliceous rocks, porcelanites, which are still highly siliceous, but a little bit less pure than cherts, and dolomites or limestones, which are made of calcium carbonate or calcium magnesium carbonate, these tend to make brittle rocks, hard, well-cemented, fracturable or brecciated brittle rocks that deform in a brittle style when deformed. Mudstones or shales regardless whether they have some silica in them or they have some carbonate in them, because of the abundant clay, are weaker rocks, and they tend to be ductile, but they also tend to extend in different ways, even when they extend and deform brittly. So this is demonstrated in this sort of conceptual block model diagram here by Michael Gross and his colleagues and students over the years. And so what you see is the Monterey, which tends to be thin bedded and very heterogeneous, where we have certain layers that are clay rich, certain layers that are silica rich, certain layers that are carbonate rich. Even though this whole area is being subject to the same strain and the same degree, well, the same stress and the same degree of strain, the same amount of extension or shortening, it's deforming in very different ways depending on the physical properties of the rock. And that difference we call the mechanical stratigraphy. So for instance, the brittle rocks like the cherts and the porcelanites and the dolomites tend to extend here in the horizontal way, in this direction. They tend to extend by bed confined opening mode fractures or joints. And you see that these fracture spacings are related to lithology, but also primarily to bed thickness. So the thinner the bed, the more closely spaced the fractures are. The thicker the bed, the more widely spaced the fractures are. If it's very thick, they're very widely spaced. Now you can have through-going fracture sets or joint swarms or fracture swarms that will go all the way through multiple beds, and these sort of form by these other fractures linking on up over time and creating a zone that's become weak and a lot of strain occurs upon them. But in this block, which is being extended, the mud-rich beds like mudstone or shale or diatomaceous rocks or something like that tend not to have these opening mode fractures, these brittle fractures, but they fail by normal faulting, by extensional faulting. And it can be completely confined to those beds, or you might see normal faulting across a mud-dominated stratigraphic interval, even if there are some thin beds that are within it that are more brittle and more silicious. So here's some great examples. On the left here in the outcrop, you see the sort of calcareous and phosphatic mudstone above and below the dark, mostly dark material here. You can see the extension there is being taken up mostly by normal faulting. You see these nice sort of conjugate normal faults, both in the lower part and the upper part. But when you go into this highly cemented brittle layer, instead of having the normal faults, all of a sudden they become vertically oriented and closely spaced opening mode fractures. So this whole rock body has been strained the same amount, but by different mechanisms because of the different properties of the rock. Now, this has some real implications in terms of fluid flow, because this kind of normal faulting in these relatively weak rocks does not very often leave open fractures that allow for fluids to migrate through them. But this brittle opening mode fracturing does, and you could see the black oil seeping out of these fractured rocks here in this particular area. This is shown here again on this side. We have a thick mudstone layer. We have a couple normal faults going through it, but the highly cemented, in this case more calcareous or dolomitic beds have the vertically oriented opening mode fracture sets. When we get into much more highly silicious rocks like cherts over here on the left, those are the white ones here. And they're white because they're the opal CT phase, not the quartz phase. And the opal CT phase tends to be a little bit more porous, and so it weathers to this white color. But now you see you're not just having those nicely spaced vertical fractures and joints, you're seeing this very irregular, almost conchoidal, choppy, blocky, angular brecciation as these rocks have been shattered by their extension. Yet when we look into the silicious shales, you're starting to see these normal faults again. So once again, these rocks are highly deforming, but by different mechanisms because they're different composition. Now, when you fault these rocks, like a through-going fault, they get offset, of course. The shale will smear, but the brecciated rocks will just be free to move and rotate as individual fragments. So over here on the right, even though we've seen more than 1 foot of displacement in this fault zone here, what you've seen is each chert zone has become highly brecciated and attenuated and dragged on down to meet its other side. So we can see the amount of offset we've had on these faults by these deformed and bent fractures. And just look how charged with oil they are, because these rocks are extremely porous due to the fracture porosity and the ability of these very, very hard, rigid fragments to rotate, yet still keep each other propped away from each other because of the strength of their angle and rough shapes. So here's another view of that same kind of thing, and this feature is quite prevalent in these more siliceous intervals here, where you can see the tremendous amount of offset. But the fact that we have these stretched, attenuated, brecciated fragments means that the fractured beds on this side of the fault, the footwall of the fault here, and the same fractured bed on the other side of the fault are still connected hydraulically and with hydrocarbons. So you can still transmit fluids through those, but in between each one of those, you're getting shale smear. So to a certain degree, this fault, even though the rocks are almost half mudstones, have not created an impermeable shale smear here in the fault zone to make it impermeable, because these really hard, brittle rocks have formed these sort of long tongues of breccias that are communicated. What's kind of cool is you see this kind of thing going on at different scales as well. So here's a seismic image that is showing, hundreds of meters, 1,000 meters across this image here, and you can see the offset. You can see the bending of the beds coming into that, the displacement, and whether or not you get communication across this fault depends upon the nature of the lithology. If they're not particularly brittle, but they're permeable and they're completely offset from one another, you'll have an impermeable barrier because you're putting permeable rocks against impermeable rocks. However, shown here very, very, very simply, if you break up that permeable layer so that there is some continuity there, then you could put fluids across this, and this will be a leaky fault that will allow hydrocarbons to still migrate across them, hopefully into a trap somewhere as well. And the same thing shown here as these rocks are attenuated as they've been offset, which is very much the case we're seeing here. But you don't think of this happening in hard, brittle rocks like a chert, but they do, because they brecciate and they weaken. So in this particular setting, it's a great insight into something we see all along California that relates to the style of deformation when we have flexural slip. And that is when you have shortening and you cause large scale folding, you are still conserving volume, and you conserve volume by having extension along the hinge or the axis of the anticline. And that extension is accommodated in different rock beds or units of rocks that are dominated by different lithologies, by different deformational mechanisms. So if it's in a mudstone dominated interval, it's normal faulting. If it's in a chert, porcelanite, or dolomite dominated interval that are hard and brittle, then you get these opening mode fractures or joints, but you're having extension, and the extension is parallel to the axis, and the shortening or contraction is perpendicular axis. And there's all kinds of evidence of this extension, from the open fractures that are filled with oil to fractures that earlier on were having fluids that were rich in calcium carbonate and precipitated calcite or dolomite in some cases. And then later the oil came on through, and you can see that there's oil here in the center of this cemented vein material. It's sort of a crack seal fracture pattern. So much fluid has gone through some of these fracture zones that it's just absolutely amazing. This is a botryoidal or mammillary calcite that is well more than a foot thick growth, band after band after band, that was allowed to grow into open space that probably was being created over time rather than that it was a big giant open void to start with. But each light colored band is relatively pure calcite with just minor amount of fluid inclusions, but each dark band is a completely hydrocarbon charged interval. So what this particular rock is showing us is that there were these alternating pulses of fluids coming up along this fault zone here that crosses across that anticline. And for a while, they had very little hydrocarbons in them, but they mostly were precipitating calcite. And then for periods, they have hydrocarbons flowing through them. And so they trap all these hydrocarbon inclusions. But not only you're precipitating cement, but the faults are moving, of course. And so this fault movement tends to shatter the brittle cement. There's a zone off to the left, and over here shown in the right, in the zone in between the calcite cement on either side of another fault zone, is a completely shattered, brecciated zone made up of the fault cement and hydrocarbons. So you're seeing periods of time of carbonate calcite cement, then oil migration, shattering of the calcite, creating a permeable breccia, more fluids flowing through there. A very complicated history, multi-phase history of fluids flow through these rocks. It's beautiful things to look at in this Arroyo Burro area, a fabulous walk to take. And so these are all good examples, if we go back to here, of how brecciated rocks, stratigraphic rocks that are very brittle, that become fractured, jointed, or brecciated, become a long strata and sometimes cross strata conduits for fluid flow and migration of hydrocarbons. Okay, so our last and third stop is at Gaviota Beach. So this is now another 34-minute drive from Arroyo Burro or the Mesa Lane Steps, heading west on the 101 and getting off at Gaviota State Park. And so our stop 3 for tonight is at Gaviota Beach. And so you come along Highway 1, you turn off here carefully across the highway, and then you come on back here and you pay your fee to come on into the campsite and the beach park. And there's the old Gaviota pier here. And although there's a great section of Monterey to the east, what we're going to be looking at here is to the west. And so here's a Dibley map of the area. Here's the access road and the pier. And so we're going to be looking at what's going on here to the west, which is blown up here in this aerial photograph, which, by the way, is from the California Coastal Record website, which flies the entire coast of California every couple of years, taking these incredibly high resolution images, which are just lovely to look at. And I use them for planning my field trips and figuring out where I'm going to climb down from the bluffs and things like that. And so they're a really great way to pre-plan your excursions to coastal areas. But what you see here is outcrops of the upper part of the Monterey Formation. And the upper part of the Monterey Formation is referred to as the clay siliceous member in this area. And it's made up most commonly of siliceous mudstone or shale and porcelanites that are thinly interbedded with a very minor amount of dolomite, concretionary dolomite. But what's unique here, and the reason we're visiting this stop here today, is there are these incised, intercalated, channelized sandstone and conglomerates that cut across the Miocene, the late Miocene slope, as slope gullies. And actually, we see a lot of these along the coast of California in the upper part of the Monterey, because you started getting tectonic reorganization, you started getting uplift inland, and you started shedding sediments down into these coarse grained sediments into the deep water. So the situation is this, that during deposition of the late Monterey. It was mostly deep water slope, but cutting across slope started becoming a sequence of narrow channels. And at Gaviota, there's 3 separate channel complexes and these slope gullies. And so they cut through, but they're entirely encased in fine-grained hemipelagic sediments, siliceous mudstones here in the Monterey, but in other places those kind of features might just be regular clastic muds. And they can be highly confined within these incised channels and not allowed to spread out very wide like a weakly confined channel system might. Today, these rocks have all been folded, of course, by the shortening, that northeast-southwest shortening, north-northeast, south-southeast shortening that's common in this fold-belt region. And here in this cross-section, you see the Monterey Formation highlighted in blue that is down at well over 15,000 feet out here, just a few miles offshore. We see some known hydrocarbon reserves right offshore here, but we have these beds dipping on up. And so we have a migration pathway. But the migration in this upper part of the Monterey is not through the Monterey because the rocks are not particularly brittle or fractured, except through these channelized deposits, these slope gully deposits. So the basic rocks of the Monterey are these ones you see in the foreground, these thin-bedded, light-colored, highly siliceous shales and porcelanites. But there in the distance, there's this dark bed that's starting to catch my eye. So this is looking west from about the pier. So you climb down under the pier and you walk out to the west. And whoa, there we go. We have the light-colored porcelanites and siliceous shales, very thin-bedded, classic hemipelagic sediments, laminated, porous, fine-grained. And then we got this black sandstones and conglomerates. And the class, the white class, the light colored class here are all Monterey class. They're cherts and porcelanites and dolomites that had been uplifted, had been deposited, buried deeply enough to undergo diagenesis, including some quartz cherts, which means at least a kilometer of burial below the surface, then uplifted inland, eroded, transported to the beach where they were rounded, and then they got bored by clams for some of the softer ones, and then they were shed back down to this water, which is upper bathyal, so probably at least 500 meters water depth, all within a few million years. That whole history of deposition in deep water, burial another kilometer, uplift a couple kilometers, erosion and transport back down deep water, all within the Monterey. This sandstone conglomerate is almost fully saturated with hydrocarbons, which have migrated up from the kitchen, from the basin, not through the regular Monterey lithologies, but through these incised, channelized deposits. This is a view where it's eroded back. This is not an anticline, it's just the way that it's eroded back, these dipping beds. But you can see the inner bedding of the mudstone shales, and then the sandstones, the mudstone shales, and then the sandstones. And some of the beds have a lot of coarse grain material in them, a lot of pebble to cobble size conglomerate as well. These are backed filled channels, so you could see the way that the internal cross stratification is dipping. It's dipping in the wrong way. So these are deposits that came down or were deposited on top of one another, backfilling the channel and filling it back on up. And here in the distance is the next channel of the 3 channel complex. So each one is about almost a half kilometer from each other. They're spread out over several kilometers along the beach here. It's really key to come here at low tide, like at about no more than about a 1 foot tide above the mean datum. You see beautiful graded low density turbidites. You see some nice burrowing going through them as well, but you also see high density turbidites and debris flows, rip up class, all kinds of things. The large class are, as you can see here, perhaps are cherts and dolomites that come from the Monterey that tell us this amazing history of rapid and deep burial, then uplift, then erosion, then transport and redeposition back in deep water again, all within just a few million years. Now, one of the things that I end up arguing with people all the time when we go on out there is about these thin oil saturated stratigraphic units. Most of them are bedding parallel. Some of them clearly look to me like they are ripple bedded, that they have cross lamination and they were deposited as ripples. And we can trace them back in some cases close to or intercepting the channels. And so I think these are overbank deposits. But the reason that they're controversial is that there are also these sandstone dikes in the area. And these are injectites. So injectites occur when you get overpressure, often from hydrocarbon generation, but sometimes just from compaction of sediments. And the pressure becomes large enough that it can overcome sigma 3, which is the minimum stress direction of the rocks, and it fractures the rock, and it can cut through it and inject it. This is a natural, ancient version of hydraulic fracturing that is both so important for hydrocarbon production in the United States right now, but also so controversial in many ways. These orientations are often very, very slightly offset from the regional fracture set, but they take advantage of the regional fracture sets as they step through the rock. So they have to follow that. So I think that's enough for an evening field trip. So you've seen now an active petroleum system in that critical moment, in the moment when the hydrocarbons are being generated from the buried organic matter, when they are migrating right now up through faults, through fractures, up along clastic channels, submarine channels. They're migrating up into structures that didn't even exist, in some cases, less than 500,000 years ago. The Ventura Avenue anticline is probably only about 500,000 years old, and yet it's been filled with enough oil, they've already produced 1 billion barrels of oil out of it. So you've seen at Carpinteria, the fracture, the migration of hydrocarbons along the damage zones of faults, the highly deformed and fractured rocks that are adjacent to the fault cores. In that case, the Red Mountain Fault, the Carpinteria Fault, and the Rincon Creek Fault. At Arroyo Burro, you saw hydrocarbon migration through fractures and brecciated rocks. You saw it going mostly along bedding, sometimes not even being disturbed by faults in highly shaly rocks, as long as you can brecciate the cherts enough to attenuate them and allow them to connect through to the other side. But then we also saw great evidence of fluid flow, both carbonate saturated waters and hydrocarbons in some larger faults that cross-cut the anticline that also on a large scale help it extend along its hinge line. And then finally in Gaviota Beach, where we saw these 3 slope gully channel deposits that went on down into the deep Paleo Basin and current deep kitchen of the Santa Barbara Channel, and has hydrocarbons migrating up through the impermeable upper Monterey rocks, but in these porous impermeable sedimentary rock channels. So with that, I hope you got your appetites whetted and you're willing to pull out your tide tables and then head on off and go look at some of this yourself. And I would encourage you to maybe consider picking up those two books or the field guides from the Pacific Section AAPG and the National SCPM, because they have a lot of great information in them, and they cover a lot more areas as well. So thank you very much.